Hello everyone, me Al-Mahdi, Ali and Yusuf, and we are going to present our work throughout this video. So let's get started. First, Diyar al-Muharrak consists of two stages. Stage 1, which already have been developed as you can see, and stage 2, which is still under reclamation work as you can see. So our project will start from this point over here, crossing the sea with a bridge, and moving towards the other side of the sea with a highway, crossing the other side of the sea with a bridge as well. And this is our scope of work. We'll cover the highway, the traffic, the drainage system design. We will go through bridge design as well, and we'll use the optimization technique, which is our main focus in this project, and we'll finalize with the design of the pond. For the highway, we have used Civil 3D to design it, and we have followed the Bahrain Road manual design standards in our calculations. And this is our main layout that we have designed in Civil 3D. Moving to the barrier, we have used a rigid barrier for the bridge, and we have used semi-rigid barriers for the roadways, and this is following the BRDM specifications. For the pavement, we have chosen type 1 pavement from BRDM options, and we have run the design using KimBave. We achieved 32 live years, which is exceed the BRDM requirement. For the intersection design, these are the locations of our junctions. A total of 3 junctions were designed and checked using CIDRA, which is the application used by Ministry of Work for the traffic design. These are the junctions from Civil 3D. And these are the junctions in CIDRA. And a level of service of B achieved which exceed BRDM requirements. And also we have done a manual calculations to compare them with CIDRA, and we have achieved similar results in both ways. Moving to the stormwater drainage system, we have used sewer gems all along with manual calculations to design it. This is a segment of the network layout that was plotted in converted from Civil 3D to sewer gems, and this is considered as network 1. And this is the whole network that was plotted and designed using sewer gems. And these are some of the results from the software, and these are some of the results by the manual calculations, and as you can see, very similar results achieved between the both ways. And for that, we have chosen the design of the program to prove it.
They're finishing the highway design, intersection design, stormwater drainage system design, pavement design, and as well as the barrier design. The question right now would be what type of a bridge system would be implemented for this project? Since the bridge is a part of a major infrastructure development in Diyar al-Muharraq, the selected bridge type had to satisfy several requirements. At the first place, it must be a structurally efficient bridge, suitable for the required span, which is in our case 270-meter span bridge, which is considered as a long span, durable, economical, and visually appropriate for the modern development area. Therefore, different bridge systems were considered and investigated in our literature review. Related to this matter, the arc bridge was selected as the most suitable option for our project due to two main reasons. First, its ability to carry the major load transfer through axial compression in the arc ribs, from the arc ribs to the abutment and to the foundation. And the second reason, which is as part of our project, that we are very interested in studying the concrete filled steel tube sections, different composite steel tube sections, which are known for its high capabilities and abilities to carry axial compressions load. So arc ribs mainly carry the load through axial compression, and the composite sections are known for its high ability to carry the axial load compression members. So we will combine the visibility of arc bridge and investigate the possibility of and efficiency of such composite sections. Slide shows the general bridge arrangement. The bridge arrangement defines the main structural configurations, including the arc ribs, deck level hangers, and support locations. The arrangement was developed based on a clear load path from the deck to the hangers, then to the arc ribs, and finally to the foundation. The selected arrangement also considers the constructability, stability of the bridge, and the required clearance for the road corridors, and integrated design for the geometry was done for the bridge, considering the highway requirements, traffic requirements, drainage system requirements. Regarding orthotropic deck steel system was adopted. This type of deck is commonly used in steel bridge structures because it is lighter than conventional reinforced concrete and precast concrete decks and provide high stiffness with efficient material use. Mentioned earlier in our presentation, one of our main objectives in this project is to investigate the efficiency and capabilities of the composite sections, mainly the concrete filled tube sections, which are, according to our literature review, are known for its high abilities to carry the loads mainly through axial compression and combined axial compression and flexure. Five different cross sections were investigated, and seven overall bridge configurations were designed, considering the effect of the inclined arcs and non-inclined arcs. Four composite sections were investigated, and one typical steel arc were investigated. Our first cross-section, which that was investigated, is the concrete-filled steel tube section. The second one is the same concrete-filled steel tube section with the effect of the reinforcement considered. The third cross-section, which was the double steel tube section, concrete-filled double steel tube sections. The fourth one, which is the concrete filled fiber reinforced tube sections, which in our case, the fiberglass fiber reinforced tube were considered. And finally, the fifth cross section, which is the typical steel arc tube. Seven different bridges were designed manually, okay, through the software design and the typical Excel sheet design. From this 7 bridge configurations, we have put a basis for comparison between the different bridge configurations, which was the cost of each bridge, the weight of each bridge, and the CO2 emissions of each bridge configuration. Out of the 7 bridge configurations, one bridge configuration would be optimized through the Metaheuristic algorithms. So, to sum up, we have 7 bridge configurations, which would be designed manually, which then would be compared to the 3 basis criteria. Out of the 7 bridge configurations, the best option that achieve the best weight, minimum weight, best minimum cost, and the minimum CO2 emissions would be chosen to be optimized using the Metaheuristic algorithms. First basis of a criteria, as we can see and compare the tilted or inclined concrete filled steel tube CFST have achieved the minimum weight among the 7 bridge configurations, or around 6,216 tons of steel. Criteria for comparison also the same. The concrete filled steel tube tilted or inclined bridge configuration also have achieved the minimum CO2 emissions among the 7 bridge configuration. For the bridge with the minimum bulk material cost among the 7 bridge configurations, also the same. The CFST tilted arc bridge was also achieved the minimum cost among the 7 bridge configurations. Manual design for the 7 bridge configurations and achieving a result that the inclined concrete filled steel tube section is the best among the 7 bridge configurations. It have been chosen to be further optimized using the Metaheuristic algorithms techniques. Optimization process. The bridge was defined using 23 different design variables and 20 increments for each variable. The variables represent the parameters that can change during the optimization process, such as the member dimensions, geometric properties, and other structural design values. The increment defines the possible steps changes for each variable. By combining variables and the increments, the algorithm can explore a wide range of different design alternatives and search for the best solution for the optimization problem. Different variables and the 20 different increments for each variable, 8.4 times 10 to the power 29 different possibilities are possible for our problem. From these possibilities, we would by the end we would reach to one possible solution out of many possible solutions, millions of possible solutions, and by the end we would compare how does this meta-heuristic algorithms could help us as a structural engineers and designers reduce our manual design in comparison with the meta-heuristic algorithms that have been used for our design problem is the artificial bee colony ABC algorithm. Diagram before running the optimization problem in combination between SAP 2000 using the API command with MATLAB. The problem in MATLAB, the best possible reduction that could we have made in comparison with our manual design is 8.33% from the original manual design structural weight. And MATLAB also have achieved a reduction in the weight equivalent to 5.65% in weight. Graphical representation for the weight reduction in our problem, 8.33% as we have stated, from 62,000 kilonewton to 56,835, equivalent to the difference between the two. 5,165 reduction in kilonewton in weight. Another graphical representation for MATLAB output, 3 different iterations. Our last chapter in this presentation would be our foundation design. The first step in our foundation design was carried using Plexus 3D. Plexus 3D supported by our manual design calculation Excel sheet for the 25-meter depth from the soil report. Representation for our soil profile Plexus 3D for our soil profile up to 25-meter depth. Output of a Plexus and the manual calculation achieving for the bearing capacity of equivalent to 170 kilonewton per meter square bearing capacity. As the superstructure design and the optimization of process, the substructure from the abutment approaches, slab, wing walls, raft, and piles were also designed for our substructures using CSI software supported with our manual design calculations. Example of our structural detailing for our substructure: a 3-meter thick raft, 171 piles, 8-meter high abutment, 2 meter in thick, by 2D structural detailing for the substructure, pile and raft. By the end, thank you. This concludes our presentation. To summarize, our project integrated infrastructure development, highway design, drainage system design, CFST archbridge design, Metaheuristic algorithms, and foundation analysis into one complete civil engineering solution for the future of Diyar al-Muharraq. This project shows how traditional civil engineering design can be improved using advanced modeling and optimization technique. By the end, thank you, evaluators, and goodbye.